Okay, so in this video we're going to talk about graph isomorphisms. And I'm going to start us off by asking the question, when do we say that two graphs are the same graphs? Okay, now if you look at the graphs G2 and G3 in this example, it's pretty clear there that even though they're drawn differently on the slide here, that they are actually the same graphs in the sense that, well, if you were to write down their vertex sets, G2, well, the vertex set of G2 is V1, V2, V3, V4, and V5. That's also the vertex set for G3. The edge set of G2, okay, well, V1 is connected to V2, V2 to V3, V3 to V4, 4 to 5, and 5 to 1. And if you look at the graph G3, 1, 2, 3, 4, 5, right? This is also exactly the same edge set there. So in terms of graphs, right, they're exactly the same graph. How about G1 though? How about G1? You're probably thinking, well, it has the same kind of structure as G2 and G3. Right? In fact, we know what these graphs are. G2 and G3, they're both just the cycle graph on 5 vertices, C5. But G1 is as well, even if it doesn't have the same vertex set, and therefore it doesn't have the same edge set as well, right? The vertex set here is A, B, C, D, E instead. And your edge set is A, B, B, C, C, D, D, E, and EA. So when we ask the question, when are two graphs the same graphs? It turns out that what we're really concerned with in graph theory is the same, meaning, do the graphs have identical structure? Right? That's what the same means here. In the sense that, well, one way to think about it is, if I were to remove all of the labels here and just not call my vertices anything, then these would be exactly the same graphs as a result. Right? Again, just drawn differently on the plane. Right? But then let's not erase. So I'm going to undo all of that. In fact, another way to think about it is we can rename the vertices of G1 to have the vertices of G2 instead and get something that's equal. Okay, so what that means is I can call this vertex my V1, call this my V2, this my V3, this my V4, and this my V5. Right, and so now they're equal if I do that renaming. Right? 1 is connected to 2, V2 to V3, and so on. And you get the exact same edge set. Right? And so notice that the way I renamed these vertices made it so that the edge sets became equal automatically. And in fact, this is how we will define what we call graph isomorphism. Two graphs, G1 and G2, with vertex sets V1 and V2 respectively, and edge sets E1 and E2 respectively, are said to be isomorphic if there is some function f from V1 to V2 such that for any two vertices in V1 that are connected by an edge in the original graph, they're also connected by an edge in the second graph G2. if you look at the action of the function f on your vertices u and v. Okay. In fact, f here has to be a bijection, right? But I mean, it has to be for this to make sense there, right? For an edge in E1 to be an edge in E2 and vice versa. So, okay, so what kind of example can we do here? Well, let's do the previous example that we just did, right? This was, what did that look like? Going down here, here, and here. And there's a star for the other one. All right, not as nice as me drawing it out, but works just as well. V1, 2, 3. Okay. And so now I can say, well, let f be a function from v1, which is the vertex set of g1, to v2, which is the vertex set of g2, defined as follows. F of a, well, what did I do for my example a while ago? F of b is v1, right? F of c is v2, and so on. And I'm just going to make it more clear here that these v1 and v2 terms up here are capital V, while these v's here are vertex names, so they're small letter v's. And so maybe I'll put like this here, just to emphasize that it's capital V for the vertex set. Okay, so that's an example of a function f, right? Such that adjacencies between vertices are preserved. And all that really means is, using this condition here for isomorphism, is that if you look at the edge AE, for instance, we know that A, comma, E is an edge in G1. Well, after you apply the function f, well, we get f of A, f of E. And this is the same as saying V5, V4. Is that an edge in E2? Yes, it is. And so under this mapping, the edge AE in G1 corresponds to the edge V5, V4 in E2. Okay, and one thing you probably see here is that this mapping is not unique. I could have defined my mapping to have brought B to V4 instead, C to V3, and then 2, 1, V5. And you'll see here that, well, okay, V5, V1 now. That's what we get here. If you apply the same condition, right? F of A is V5, F of E is V1. So all that does is now map these edges to each other using F. And it still works. It's just another way of doing that renaming, right? So that you get this isomorphism between the two graphs. That proves that they do have the same structure. 5 vertices each, and connected using a 5 cycle. Now, that actually gives us an easy way to check or to verify that a graph is not isomorphic to another. Right, so if I give you a graph that looks like this, for instance, let's see. And then I give you another graph that looks like this on the right. Well, you can immediately say they're not isomorphic, right? There's no way they have the same structure if you have 8 vertices on the left and 6 vertices on the right. Now, even if I match the number of vertices, right? So now I have 8 vertices here and 8 here. Well, you can still tell me that they're not going to be isomorphic to one another. Just count the number of edges. Right? Here you have 8 edges down here. And up here you have, well, that's 12. So there's no way you can define any function from the vertices of G1 to the vertices of G2 so that edge adjacencies are preserved. Right? Or vertex adjacencies are preserved. In fact, we can go even further than that, than just saying number of edges. Right? We can actually check degree sequences. This is 3, 3, so this is actually all 3s. Here it's all 2s. So you're inevitably going to get some edges in E1 such that whatever they're mapped to in E2 are not edges. Now I just want to end by saying the following, that if two graphs have the same degree sequence, do you think it follows that they're isomorphic? And if so, can you argue why? Or if not, can you give an example of two graphs that have the same degree sequence but are not isomorphic?